Hey everyone, and welcome back to the channel. I'm absolutely thrilled to share this comprehensive Keras tutorial with you today. If you've ever wanted to dive into deep learning but found TensorFlow intimidating, or if you're curious about building neural networks without getting lost in complex code, then you're in the right place. In the next hour, we're going on a complete journey through Keras, from absolute beginner to building advanced neural networks like GANs. I'm talking about going from what is Keras to actually deploying your own AI models. We'll cover everything hands-on with real code examples. By the end of this video, you'll have built your first neural network, understood how to train it, and even learned about cutting-edge techniques like transfer learning. If this sounds exciting, hit that like button now. It really helps the algorithm share this with other aspiring AI developers. And definitely subscribe if you're new here, because we publish tutorials like this every week. All right, let's dive in and demystify deep learning together. So, what exactly is Keras? Let me paint you a picture here. Imagine you want to build a house. TensorFlow is like having all the raw materials: bricks, cement, steel beams. It's incredibly powerful, but you need to know exactly how to put everything together. Keras is like having a skilled architect who can take those materials and help you build your house with simple, clear instructions. Keras is a high-level neural networks API. The keyword here is high-level. It abstracts away all the complex mathematical operations and gives you simple, intuitive functions to work with. And here's the beauty. Since Keras runs on top of TensorFlow, you get all of Google's industrial-strength machine learning capabilities, but with a much friendlier interface. It's like driving a luxury car. You don't need to understand the engine to enjoy the smooth ride. The syntax is so clean and readable that you can often understand what a neural network does just by looking at the code. But don't mistake simplicity for lack of power. You can build everything from basic classifiers to complex GANs with Keras. And we're not talking about some academic toy here. Companies like Netflix use Keras for their recommendation systems, Uber uses it for demand forecasting, and Airbnb uses it for dynamic pricing. This is production-ready technology. But enough theory. Let's get our hands dirty and actually install this magic. All right, installation time. And I have great news. This is probably the easiest deep learning framework you'll ever install. Here's the method I recommend for 99% of users. It's just one simple command: pip install TensorFlow. Now, there is a standalone Keras installation option available, but honestly, unless you have very specific requirements, stick with the first method I just showed you. When you run this command, the installation will take a few minutes depending on your internet connection. TensorFlow is a fairly large package because it includes optimized libraries for both CPU and GPU computation. Installation done? Let's talk about the next crucial step: verification. Once the installation finishes, we need to verify everything works correctly. This verification step is crucial. It's like checking that your tools work before starting a project. This simple code does three things: imports TensorFlow, imports Keras from TensorFlow, and prints out both version numbers. Perfect. When you run this code, you should see version numbers like these. If you see TensorFlow 2.0 and Keras integrated seamlessly like this, you're ready to go. And that's it for installation. In just one command, you now have one of the most powerful deep learning frameworks at your fingertips. Now that we have Keras installed, let's understand how it works. Keras gives you 3 different ways to build models, and choosing the right one depends on what you're trying to achieve. First up is the Sequential API. This is your starting point. Think of it like stacking Lego blocks. Each layer sits on top of the previous one. Data flows in a straight line from input to output. Look at this code example. We create a sequential model and pass it a list of layers. First, we have a dense layer with 64 neurons and ReLU activation, then another dense layer with 10 neurons and softmax activation. This creates a simple feed-forward network. The first layer has 64 neurons, perfect for learning complex patterns. The ReLU activation function helps the network learn nonlinear relationships. The second layer outputs 10 probabilities, great for classifying 10 different categories. But what if you need something more complex? That's where the functional API shines. Instead of a simple stack, you can create networks with branches, multiple inputs, or multiple outputs. See how different this looks? We explicitly define the input shape, then we apply layers by calling them like functions. This approach lets you create complex architectures like ResNet or inception networks. And for the ultimate control freaks, myself included sometimes, there's model subclassing. This lets you define exactly how data flows through your network. Perfect for research or when you need custom training loops. One thing I love about Keras is the built-in metrics. You get accuracy, loss tracking, precision, recall, all the evaluation tools you need without writing custom code. Now, let's put this theory into practice and build our first real neural network. All right, this is where the magic happens. We're going to build a neural network from scratch that can recognize handwritten digits. This is like the hello world of deep learning. Let's break down this code step by step because understanding each piece is crucial. First, we import what we need. Sequential for our model structure, dense for fully connected layers, and dropout for preventing overfitting. We'll talk about that in a moment. Now let's build our network layer by layer. The first layer has 128 neurons. I chose this number because it's large enough to capture complex patterns, but not so large that training becomes slow. The input shape equals 784, tells Keras to expect 784 features. Why 784? Because we're working with 28 by 28 pixel images, and 28 times 28 equals 784. We flatten the 2D image into a 1D array. ReLU activation is crucial here. It stands for Rectified Linear Unit. Basically, it outputs the input if it's positive, otherwise 0. This helps the network learn complex nonlinear patterns. These dropout layers are like adding controlled chaos to prevent overfitting. During training, they randomly set 20% of neurons to 0. This forces the network to not rely too heavily on any single neuron. The final layer has 10 neurons with softmax activation, perfect for our 10-digit classes, 0 to 9. Softmax converts the outputs into probabilities that sum to 1. Compilation is where we tell Keras how to train the model. Atom Optimizer is like having a smart learning algorithm that adjusts the learning rate automatically. Categorical cross-entropy is perfect for multi-class classification problems. Look at this visual representation. Data flows from the 784 input features through hidden layers that learn increasingly complex patterns, finally outputting probabilities for each digit class. The model.summary command is incredibly useful. It shows you exactly what your network looks like, how many parameters it has, and helps you spot potential issues before training. Think of neural network layers like tools in a toolbox. Each layer type is designed for specific tasks, and knowing which tool to use is half the battle. Dense layers are your Swiss Army knife, useful for almost everything. Every neuron in one layer connects to every neuron in the next. This creates 64 neurons, each receiving input from all previous neurons. It's like having a committee where everyone talks to everyone else. Great for learning complex relationships in tabular data. But for images, we have something much more powerful:
convolutional layers. These are game changers for computer vision. This creates 32 filters, each scanning the image with a 3x3 window. Think of it like having 32 different detectors. One might detect edges, another might detect corners, another might detect textures. Imagine you're looking for specific patterns in a Where's Waldo puzzle. Instead of examining every pixel individually, you use small windows to scan for red stripes, round glasses, specific shapes. That's exactly what Conv 2D layers do. For sequential data, text, speech, time series, we have LSTM layers. These have memory. LSTM stands for long short-term memory. Unlike regular layers that treat each input independently, LSTMs remember previous inputs, perfect for understanding sentences where context matters. For example, in the sentence, "The movie was not bad," the word "not" completely changes the meaning. LSTMs can remember "not" when processing "bad" and understand the overall sentiment. And our friend Dropout. This isn't really a computational layer, it's more like a training technique. During training, it randomly ignores 20% of neurons, forcing the network to be more robust. Now, here's where it gets exciting: combining layers for real-world tasks. This is a classic CNN architecture. We start with convolution to detect features, max pooling to reduce size, flatten to convert 2D to 1D, then dense layers for final classification. It's like an assembly line. Each layer has a specific job.
All right, we've built our model. Now comes the exciting part, teaching it to recognize patterns. This is where your computer becomes a learning machine. First, data preparation. This step is crucial. We're using the MNIST dataset, which contains 70,000 images of handwritten digits. It's like the fruit fly of deep learning, perfect for learning. Notice the reshape -1, 784. We're flattening each 28 by 28 image into a 784 element vector. The -1 tells NumPy to figure out the first dimension automatically. Then we divide by 255.0. This normalizes pixel values from 0 to 255 range to 0 to 1 range. Neural networks love data scale to small ranges. The 2 categorical converts labels like 3 into 0001000000, called one-hot encoding. It's like having separate yes-no switches for each digit class. Now, the moment of truth, model.fit. This single command contains so much power. Batch size of 32 means we show the model 32 images at once. Why not one at a time? Because processing in batches is much more efficient, like washing dishes in batches rather than one by one. Epochs equals 10 means the model will see the entire dataset 10 times. Each time through, it gets a little bit better at recognizing patterns. Validation split point 2 is crucial. It sets aside 20% of training data to test the model during training. This helps us catch overfitting early. These parameters are like the knobs on a radio. You tune them to get the best performance. Batch size affects memory usage and training stability. Epochs control how long you train. Too few and the model underfits. Too many and it overfits. After training, we evaluate on completely unseen test data. This is like the final exam. It tells us how well our model will perform in the real world. What's actually happening during training? The model makes predictions, compares them to correct answers, calculates how wrong it was, then adjusts its internal parameters slightly. Multiply this by millions of examples and gradually it learns. With this simple setup, you'll typically get 95% accuracy on handwritten digits. That means your model correctly identifies 19 out of every 20 handwritten digits. Okay, now we're entering the really cool territory, generative adversarial networks, or GANs. This is where AI becomes truly creative. Imagine 2 artists in competition. One artist, let's call them the generator, tries to create fake paintings that look like real Van Goghs. The other artist, the discriminator, is an art expert trying to spot the fakes. As they compete, both get better and better. Look at this visualization. The generator takes random noise, just random numbers, and tries to turn it into realistic images.
The discriminator looks at both real images and generated images and tries to tell them apart. The generator is fascinating. It starts with 100 random numbers, pure noise, and gradually expands this through larger and larger layers until we get 784 outputs representing a 28 by 28 image size. Notice the tan activation on the final layer? That outputs values between -1 and 1, which works well for image generation. The reshape at the end converts our flat 784 numbers back into a proper 28 by 28 image size. The discriminator is like a detective. It takes an image, flattens it, processes it through dense layers, and outputs a single probability. Is this image real or fake? Here's where it gets mind-blowing. During training, we play these networks against each other. The generator tries to fool the discriminator tries not to be fooled. This adversarial training creates incredibly realistic results. GANs aren't just academic curiosities. They're used to generate faces for video games, create art, enhance low-resolution images, and even generate realistic synthetic data for training other models. This sword represents the adversarial process. It's like an arms race where both sides keep getting better. The result? Generated images that are so realistic, humans can't tell them apart from real photos. And the best part? All of this complex adversarial training is possible with just a few dozen lines of Keras code. Building a model is just the beginning. The real art is in evaluation and fine-tuning to squeeze out every bit of performance. This separates the hobbyists from the professionals. Don't just stop at basic accuracy. This gives you a single number, but you need to understand where your model is struggling. This classification report is gold. It shows precision and recall for each class. Maybe your model is great at recognizing zeros and ones, but terrible at 8s and 9s. You need to know this. But numbers only tell part of the story. Visualization is crucial. These plots are your diagnostic tools. If training loss keeps decreasing, but validation loss starts increasing, you're overfitting. It's like studying so hard for that one specific test that you can't handle similar but different questions. This is where callbacks become your best friends. They're like having automated assistants watching your training. This callback watches validation loss. If it stops improving for 3 epochs, it cuts the learning rate in half. It's like switching from big steps to small steps when you're close to your destination. Model checkpointing is like having autosave in a video game. It saves your best model automatically so you never lose your progress. Fine-tuning is an iterative art. You train, evaluate, analyze the results, adjust hyperparameters, and repeat. Sometimes changing the learning rate from 0.001 to 0.005 can boost accuracy by 5%. Pro tip, always use early stopping to prevent overfitting, and always keep a holdout test set that your model never sees during development. This gives you an honest assessment of real-world performance.
Now we're entering professional territory, the techniques that bridge the gap between academic experiments and production systems used by major tech companies. Transfer learning is absolute magic. Instead of training from scratch, you take a model trained on millions of images and adapt it to your specific task. VGG16 was trained on ImageNet, 14 million images across thousands of categories. It already knows how to detect edges, shapes, textures, and complex patterns. Why throw that knowledge away? By setting trainable equals false, we freeze these pre-trained layers. We're saying, keep your knowledge about basic visual features, just let me teach you about my specific problem. Then we add our custom layers on top. It's like hiring an expert photographer and asking them to specialize in wedding photography. They already know about lighting and composition. But what good is a model if it sits on your laptop? Deployment is where your AI meets the real world. TensorFlow Lite is incredible for mobile deployment. It compresses your model and optimizes it for smartphones and IoT devices. Your neural network can run on a phone with minimal battery impact. For cutting-edge research, you might need custom training loops with complete control over the training process. This gives you surgical precision over training. You can implement custom loss functions, complex learning schedules, or novel training techniques that haven't been implemented in high-level APIs yet. These research areas represent the cutting edge of AI.
Style transfer creates artistic images. Attention mechanisms power language models like GPT. Transformers revolutionized natural language processing, and reinforcement learning is creating AI that can beat humans at complex games. The beautiful thing about Keras is that it grows with you. Start simple, but know that you can tackle any of these advanced topics when you're ready. All right, time to test your knowledge. Don't worry, this isn't a pop quiz for grades. It's just to reinforce what we've learned and make sure that key concepts are sticking. If you're following along on the interactive slides, go ahead and click your answers. If you're just watching, pause and think about each question. Question 1. Which API is best for beginners? Take a moment to think about what we discussed. The answer is B, Sequential API. Remember our Lego analogy? Sequential is perfect when you're stacking layers in a simple, linear fashion. It's intuitive and covers 80% of use cases. Question 2. What does dropout prevent? This is an important concept. B. Overfitting. Dropout adds controlled randomness during training, forcing the network to be more robust and not rely too heavily on specific neurons. It's like cross-training in athletics. Makes you more well-rounded. Question 3. Which layer is best for image processing? B. Conv2D. Convolutional layers are specifically designed for spatial data like images. They use local receptive fields and shared parameters to detect features efficiently. Dense layers would work, but would be inefficient and miss spatial relationships. How did you do? Don't worry if you didn't get them all. Learning is a process. Speaking of learning processes, you don't have to do this alone. The Keras community is incredibly welcoming and supportive. The official documentation at keras.io is fantastic. Well-written, lots of examples, and regularly updated. The TensorFlow forum is great for getting help with specific problems. If you want to go deeper, I highly recommend Deep Learning with Python by Francois Collet. He's the creator of Keras, so you're learning from the master himself. The Fast.ai course is also excellent for practical applications. And don't forget about GitHub. The Keras Examples repository has implementations of almost every major neural network architecture. It's like a cookbook for deep learning. Remember, every expert was once a beginner. The key is to start building, experimenting, and learning from both successes and failures. The community is there to help you when you get stuck. Wow! Look at everything we've accomplished together in this session. We started with what is Keras, and now you understand installation, model building with both sequential and functional APIs, popular layer types, training processes, evaluation techniques, advanced topics like GANs and transfer learning, and even deployment strategies. This isn't just theoretical knowledge. You now have practical skills that companies like Netflix, Uber, and Airbnb use in production systems. But learning doesn't stop here. Here's your homework, and I really mean it, because the only way to truly learn deep learning is by doing. Start with the MNIST digit classifier. That's your hello world moment. Once you get 95% plus accuracy on that, try CFAR 10 for color image classification. Then experiment with text processing using LSTMs or transformers. I'm giving you a complete starter project right here. This code will get you started with handwritten digit recognition. Copy this code, run it, modify it, break it, fix it. That's how you learn. Try changing the number of neurons, add more layers, experiment with different activation functions. Remember, you're not just learning a tool, you're learning to think like an AI engineer. The patterns and concepts you've learned today apply to every major deep learning framework. If this tutorial helped you, hit that like button. It really does help other aspiring AI developers find this content. And if you're new here, definitely subscribe because we're releasing in-depth tutorials like this every week. But most importantly, I want to hear from you. Drop a comment below and tell me, what's the first neural network you're going to build? What problem do you want to solve with AI? What deep learning topics should I cover next?
And if you build something cool with what you learned today, share it in the comments or tag me on social media. I love seeing your projects and celebrating your wins. The AI revolution is happening right now, and you're no longer just watching from the sidelines. You're equipped to be part of it. Every neural network you build, every model you train, every problem you solve is making you more valuable in this exciting field. So go forth, build amazing things, and remember, the future belongs to those who can teach machines to learn. You're now one of those people. Thanks for spending your time learning with me today. Until next week, keep coding, keep learning, and keep building the future.